Good morning, my dear students. In the previous class, we have discussed about conformational isomerism and we saw the conformations exhibited by butane molecule and cyclohexane. We continue our discussion with cycloalkanes and Bayes strain theory. Now see here, these are the cycloalkanes. Cycloalkanes are saturated alkane molecules which exist in a cyclic form. For any compound to be in a cyclic form, it should have three corners to form a cyclic structure. Hence, cyclopropane is the first cycloalkane, that is C3H6 is the first cycloalkane, that is cyclopropane. The structure is shown here, followed by cyclobutane, cyclopentane, cyclohexane, etc. When we observe these cycloalkanes, all these cycloalkanes are saturated compounds. That means these cyclocompounds or cycloalkanes does not have multiple bonds. That means the hybridization of each carbon atom of any cycloalkane is 109 degree 28 minutes, because for any sp3 hybridization we expect the bond angle is to be 109 degree 28 minutes, and for any sp3 hybridization the shape or geometry should be tetrahedral. But when we observe these cycloalkanes, none of these compounds have a bond angle of 109 degree 28 minutes. That means all these cycloalkanes are deviating from the tetrahedral bond angle. That means these molecules have some strain in their ring structure. From 109 degree 28 minutes, the bond angles are decreased. Hence, these molecules are less stable compared to alkanes, open chain compounds. Baer, the scientist, studied about these deviation in bond angle from 109 degree 28 minutes, and he proposed the famous theory called Bayes strain theory. Bayes strain theory. It was observed that Cycloalkanes are usually stable, even though bond angle is not 109 degree 28 minutes. To explain the stability of cycloalkanes, Adolf von Baer proposed a theory, and it is called Bayes strain theory. He proposed certain postulates to explain why cycloalkanes are stable even though the bond angle is not 109 degree 28 minutes. Some of the cycloalkanes are highly stable, while some of the cycloalkanes are least stable. And this stability of cycloalkanes could be explained using Bayes strain theory. The first postulate of Bayes strain theory is that the molecule is planar. That means for any cycloalkane, all the carbon atoms lie in one plane. So, all cycloalkanes are planar molecule. The second postulate says that when a cycloalkane deviates from the tetrahedral bond angle of 109 degree 28 minutes, it causes a strain to the cycloalkane, and that strain is designated as angle strain. So angle strain is the strain caused to the ring structure of cycloalkanes due to the deviation from its normal tetrahedral bond angle of 109 degree 28 minutes. The third postulate says that greater the angle strain, lesser the stability, or greater the instability. For any cycloalkane, we could compute the angle strain, and greater the angle strain, that cycloalkane will be less stable. And finally, he proposed any cycloalkane with higher stability could be easily synthesized or could be easily prepared. These are the main postulates of Bayes strain theory. Now see here, we are going to calculate the angle strain for cyclopropane. See here we have a CH2, CH2, CH2 group in the corners of this triangle. Or we could say cyclopropane consists of 3 CH2 group at the 3 corners of that planar structure. That means cyclopropane is a planar structure. And when we calculate the bond angle is found to be 60 degree. But this CH2 group is tetrahedral in hybridization. Hence, the bond angle should be 109 degree 28 minutes. From the 109 degree 28 minutes, we are bringing the bond angle to 60 degree. That means from both sides we are limiting the bond angle of 24 degree 24 minutes to 60 degree. Hence, the angle strain of this molecule is half into expected tetrahedral angle minus actual angle, that is 24.44 minutes. So, for cyclopropane, the angle strain is 24.44. That means the molecule is strained by an angle of 24.44 degree. Now see here, they have calculated many cycloalkanes angle strain. So the angle strain of cyclobutane is found to be 9 degree. The angle strain of cyclopentane is found to be 44 minutes. The cyclohexane is minus, that means the bond angle is extending from 109 degree to 120 degree. So the angle strain for these molecules could be calculated by Bayes strain theory. Take down. So using Bayes theory, we could explain why cyclobutane is more stable than cyclopropane. So when we consider the deviation of angle from the normal tetrahedral angle, in case of cyclopropane, the angle deviation is found to be 49 degree 55 minutes, because the bond angle of cyclopropane is 60 degree. So actual expected tetrahedral bond angle is 109 degree. So the difference is 49.5 degree. This clearly shows that the deviation is maximum for cyclopropane. Moving to the case of cyclobutane, the bond angle is found to be 90 degree. So 109 minus 90, that is equal to 19.5. 19.5. Now comparing the deviation of cyclopropane and cyclobutane, the deviation of cyclopropane is maximum, while that of butane is lower or less than cyclopropane. Hence, the strain is maximum for cyclopropane. That is why cyclopropane is highly unstable and it easily undergoes ring opening reactions, while cyclobutane does not easily undergo ring opening reaction. So Bayes theory could explain why cyclopropane is less stable while cyclobutane is more stable. So on the basis of Bayes theory, we expect cyclopentane is having maximum stability, because see here, the strain, the angle strain is minimum for cyclopentane. Then cyclohexane, cyclobutane, cyclopropane. But experimentally it is observed that cyclohexane is more stable than cyclopentane, which is more stable than cyclobutane, which is more stable than cyclopropane. So the high stability of cyclohexane is due to the conformation of cyclohexane into chair or boat form. So from the table of angle strain, the angle strain is minimum for cyclopentane. But it is observed that cyclopentane is less stable than cyclohexane. Or we could say the highest stable cycloalkane is cyclohexane. So remember the order. Cyclohexane is more stable, then cyclopentane, then cyclobutane, and least stable is cyclopropane. So it is shown here, angle strain. This is the actual angles. So least stable is this one, and the most stable is cyclohexane. Take down. Now moving to the limitations of Bayes strain theory. Even though Bayer was able to explain the stability of many cycloalkanes, he failed to explain the stability with the angle strain to bigger ring systems. He failed to explain why cyclohexane is more stable than cyclopentane, even though the angle strain is in reverse manner. Many of the higher cycloalkanes have negative angle strain, but they exist and are highly stable. Bayer was not able to explain why it is happening so. As per Bayes strain theory, all the cycloalkanes are planar systems. But moving to cyclohexane, cycloheptane, etc., the systems are not planar. They are puckered, or they could say they have different conformations. So he failed to explain these for the stability of cycloalkanes. Take down. Now we move to another topic, that is optical isomerism. We know what is isomerism, and isomerism is basically classified into two. They are structural isomerism and stereoisomerism. In stereoisomerism, we have geometrical isomerism and optical isomerism. Moving to optical isomerism, we have to see a term called plane polarized light. What is a plane polarized light? Ordinary light is having infinite direction of vibration, but plane polarized light has only one direction of vibration. When ordinary light is allowed to pass through a Nicol prism, that Nicol prism will cancel all directions of vibrations except one. And this light, whose vibration occurs only in one plane, is called plane polarized light. So an optical compound behave with plane polarized light in different fashion. Now we have to see what is optical activity. Some substances have the ability to rotate the plane polarized light either towards left direction or towards right direction. This property is called optical activity, and such substances are called optically active substance. So, optical activity is defined as the process or phenomenon by which a compound rotates the plane polarized light either to the left direction or to the right direction. That property is called optical activity, and the substance which shows optical activity is called optical active compounds. Then we define what is optical isomerism. Optical isomerism is the process or phenomenon by which molecules have same molecular formula and same structural formula, but their behavior towards plane polarized light is different. So, two compounds are found to be optical isomers. They have same molecular formula, same structural formula, but one isomer rotate the plane polarized light towards left while another rotate the plane polarized towards right. This difference in behavior towards plane polarized light is called optical isomerism. If the substance rotate the plane polarized light towards left, it is called levorotatory or L form. Levorotatory or L form. If the isomer rotate the plane polarized light towards right, it is called dextrorotatory or D form. So, optical isomers could be of two types, levorotatory or dextrorotatory. Take down. Now moving to the details of optical isomerism, we have to think about chiral centers. It is a point in the molecule where there should be a carbon atom and four different groups or group of atoms should be attached. So if in any molecule there is a carbon atom with four different groups or group of atoms attached, it is a chiral center. And a chiral molecule usually should have minimum one chiral center. If the molecule is having chiral center, it will be an optically active compound. See here, in this particular molecule, this carbon atom is attached to four different groups. One is bromine, one is H, one is ethyl group, and one is propyl group. So we could say this is a chiral carbon atom or chiral center, or it is also called as a stereogenic center. Stereogenic center. So the presence of a stereogenic center is a condition for a compound to show optical isomerism. So, chirality is a condition for a molecule to show optical isomerism. So, that stereogenic center or chirality center is also called as asymmetric center, and that carbon is called asymmetric carbon atom. That means the molecule should contain an asymmetric carbon atom. If it contains an asymmetric carbon atom and if it gives rise to a chiral molecule, then that compound will exhibit optical isomerism. So we could say asymmetric carbon atom or asymmetric center is a carbon atom in which all the four substituents are different group or group of atom. Such molecule and such molecules which have asymmetric carbon atom, and if the molecule is chiral, the molecule exhibit isomerism, that is optical isomerism. Now you just see here, I have a right hand here, and if I see this right hand in a mirror, it appears like the left hand, and this right hand and left hand forms non-superimposable object to mirror image connection. That means the object and the mirror image does not undergo superimposition. Hence, this object is chiral, and the phenomenon is called chirality. So, chirality is defined as the process or phenomenon by which an object or molecule forms non-superimposable object mirror images. Now see here, this chair. Chair is an example for a achiral object because the object and the mirror image undergoes superimposition. That means they are superimposable. So the object and mirror images are superimposable. Hence, it is an example for a achiral objects. Molecules which have chirality, that means molecules which forms non-superimposable object mirror images, exhibit optical isomerism. Or we could say any molecule with chirality shows optical isomerism. So we have seen what is chirality and what are chiral molecules. And I told you a molecule that is not superimposable to its mirror image is said to be chiral. And for an organic molecule to be chiral, it should have a carbon atom with four atoms or group of atoms present in it. It is called as a chiral center or stereogenic center or chirality centers. For example, you see in lactic acid, this is lactic acid and this is the central carbon atom, and this chiral carbon atom or stereogenic center or asymmetric carbon atom or chirality center have four different groups. One group is CH3, one is OH, one is H, and another is COOH. So for any molecule, if it is having a chirality center or stereogenic center, and if it forms non-superimposable mirror image, object to mirror image, we could say the molecule exhibit chirality and usually optical active. From our discussion, we could summarize the two necessary conditions for any compound to be optically active or to exhibit optical isomerism are: 1. The molecule must have a asymmetric carbon atom or a chiral center or a stereogenic center. The second condition is that the mirror image of the molecule must be non-superimposable, or we could say the object and its mirror image should be non-superimposable. If any molecule satisfies these two conditions, that molecule exhibits optical isomerism. That means that molecule should lack symmetry elements. If the molecule does not have any symmetry element, it gives rise to objective non-superimposable mirror image, and hence the molecule becomes optically active. An object lacking a plane of symmetry is called disymmetry or chiral symmetry, disymmetry. Now see here, this is lactic acid. Lactic acid exhibits optical isomerism because if I take this as the object and this as the mirror image, these two form non-superimposable mirror images. So both these forms are existing. This form is existing, this form is existing. These two forms are connected or related as non-superimposable object to mirror images. And this molecule does not have any symmetry elements. And this molecule is having a chirality center. So all the conditions are satisfied, and hence lactic acid, if this is plus lactic acid or D-lactic acid, this will be L-lactic acid or minus lactic acid. If this is levo, this will be dextro. So these two forms are existing in three-dimensional picture, but they are related as object to mirror images. Take down. So we have defined the conditions for a molecule to be optically active. Now we move to another term called enantiomers. What are enantiomers? Enantiomers are basically optical isomers. They are related as object to mirror image. As I told you earlier, there are two different molecules or two different optical isomers and they are related as object to mirror image. That means enantiomers are compounds having same molecular formula and they are connected as non-superimposable object to mirror image relation. Such pairs which are considered or related as object to mirror image are called enantiomers. When we consider the enantiomer, one enantiomer may be dextrorotatory, then another enantiomer would be levorotatory. If one enantiomer is levorotatory, the another enantiomer should be dextrorotatory. See here, this is an example that I showed you earlier. This is lactic acid. This is the mirror image of lactic acid. These two are non-superimposable to each other. But see here, this molecule is existing and this molecule is existing. They have same molecular formula, same structural formula, but the spatial arrangement is different. Due to this different spatial arrangement, they are related as non-superimposable object to mirror image. Such pairs are called enantiomers. Very important. Take down. So, thank you, my dear students. Take down the notes and we will continue our discussion with the optical isomerism in the next class. Thank you. Thank you very much.